Hello, everyone. My paper is real-time control of a low-cost robotic arm using EMG signal classification by AI-based machine learning on Raspberry Pi. Here are the co-authors of this paper. My name is Raeyaan Muppaneni from YRI Fellowship, and I'll be taking you through this paper. We'll be going through the abstract, introduction, related work, the methodology I used for this research, the results, conclusion, and scope for future work. There are more than 804.5 million elderly people who need support for normal functioning of their daily routine, and 1 in 3 of these people suffer from some form of a neurological condition. This paper presents a low-cost bionic robotic arm that mimics 3 basic motions in the hand. These are hand lift, hand twist, and wrist lift. I also collected data for normal position. The motion data was acquired using an ESP32 controller along with a MyAware Surface EMG sensor. The data was transmitted over Wi-Fi using MQTT protocol to a Python server. I evaluated 3 pipelines: raw EMG envelope, TS-Fresh statistical features, and MFCC features. Among KNN, random forest, and MLP and SVM models, random forest achieved the highest performance and was deployed on a Raspberry Pi for real-time inference and controlling the servo-based robotic arm. In device trials, the deployed model achieved up to 93% test accuracy. The global impact of this work is that it helps aid those who have motor dysfunction, which is over 804.5 million people worldwide. And these dysfunctions can often stem from conditions like Parkinson's disease, strokes, or spinal cord injuries. Additionally, there are amputees who've lost mobility in their arm, and this prosthetic-like device can restore that motion. The current limitations in the field right now are that the traditional treatments and mechanical aids are often blocked by high cost, limited accessibility, and a lack of real-time responsiveness in the devices. So a bit on the actual surface EMG technology. So surface electromyography captures electrical activity from skeletal muscles to detect residual motor intent non-invasively. More simply put, this just takes muscle signals from the human arm as electrical signals that can be interpreted. The goal of this project was to design an affordable, adaptable, and real-time control system for individuals with motor dysfunction. Now, going on to the related work, classical approaches to previous surface EMG decoding has relied on more classical features and shallow classifiers, such as KNN, SVM, and random forest, which offer low computational costs. However, more recent studies have shifted towards deep architectures like CNN and RNN, which process the raw signals directly and often achieve a higher accuracy. However, the trade-off with CNN and RNN and these deeper architectures is that they demand more energy and memory, which makes them more difficult to deploy on embedded hardware, as well as not working as quickly in real time. The focus of this specific research was to prioritize the feasibility and real-time control, as well as maintaining a low cost rather than getting a higher accuracy. So I decided to focus more on the classical shallow classifiers, KNN, SVM, random forest, and MLP. So for the methodology, for the hardware setup, I used an ESP32 microcontroller, MyAware EMG sensor, a Raspberry Pi Model 4, and servo motors, which were connected at the joints of the robotic arm. For the data acquisition, I collected 4 different motions: hand lift, hand twist, normal position, and wrist lift. I collected 70 samples for each motion in 250 millisecond non-overlapping windows. Now, for the signal processing, EMG data is actually really noisy. So what I did to get clean values was I applied a moving average filter, which removes all these like high noise and spikes. And then I used a full wave rectification, which makes all the values positive. That way we're only looking at the magnitude of the EMG data. And then the low pass Butterworth filter creates smooth values rather than the spikiness of the EMG data. And from this, I got the EMG envelope data. Then I used feature extraction software, specifically TS-Fresh and MFCC, to extract features from the raw envelope data. And from there, I had 3 different data sets, Fresh and MFCC. Now, for real-time control, I used a Raspberry Pi, which took the train model, the final model, which I found to be the most efficient, and then it classified the motions and then incrementally controlled the servo-based robotic arm with these classifications. So for the results, I found that for offline validation, the MLP achieved the highest offline validation accuracy of around 84% using TS Fresh, while SVM peaked at about 80% on TS Fresh statistics. And then KNN actually had a stable baseline, reaching 80% validation accuracy on MFCC features. Now for real-time deployment, however, the results showed that random forest model performed the best for EMG envelope data, achieving a 93% accuracy on the prototype. Looking at this graph here, this is a comparison of the hyperparameters of the random forest model in comparisons to accuracy. So estimators and depth are the two hyperparameters for the random forest model. From the graph, we can see that a depth of 5, which is the green line right here, seems to be the highest in terms of accuracy. So I decided to take a depth of 5. And then for estimators, I took around 20 because that's where the accuracy seemed to peak around and be more consistent. Additionally, I want to make sure the hyperparameter value was lower so that it was more efficient on time. So for the conclusion, from this project, I was able to successfully create a functioning low-cost EMG-based robotic arm system that used machine learning. And the results of this project demonstrated that while complex features like TS Fresh and MFCC do have the ability to improve metrics like accuracy, simpler raw EMG envelope values combined with a random forest model are good enough for a robust real-time embedded environment. Additionally, this research proved that accessible low-cost hardware can be effectively utilized for smart prosthetics and customized rehabilitation. Future scope. So in the future, I plan to expand this data. Right now, I only have 70 samples for each different motion. However, in the future, I plan to extend this to maybe 100 samples or even 200 samples. Another thing I could do in terms of data expansion is collecting data from more than one person's hand. So currently in this research, I collected the data from only my arm. But if we were to collect it from a diverse amount of people's arms, then that would reduce bias in the data. That way, it's more universally usable. Additionally, another thing that can be fixed is user calibration. Right now, how I've coded the robotic arm is so that it has one direct motion from point A to point B rather than gradual motion, which is what you would want for an ideal prosthetic that is user-friendly. So having incremental motion is another improvement for the future. As for the model architecture, I could explore more hybrid architectures to balance accuracy and computational efficiency. In this one, we use like KNN random forest, which focused more on computation efficiency, and the trade-off was accuracy. But the other alternative to that was RNN and CNN, which sacrifice computation efficiency for accuracy. So maybe finding a balance between these two would provide the optimal device. Additionally, for hardware refinement, you could optimize the hardware. And in terms of the hardware, I'm talking about the actual robotic arm here. Generally, you want a robotic arm that uses energy conservatively, efficiently. That way, the cost is also minimized. Additionally, you want a prosthetic or real robotic arm to avoid jerky motion. So these are things that can be optimized to provide the ideal prosthetic. Thank you for listening.